For the last part of Chapter 6, I want to talk about a concept known as a departure function. And to demonstrate this, I want to talk about one of our trusty model systems, the turbine. And what we're going to do is we're going to consider a turbine that has a gas passing through it, and that gas can be methane. And so for our turbine, what we have is for the inlet stream, we have 1 mole per second of methane. It's at a pressure of 10 bar and a temperature of 600 Kelvin. The methane passes through the turbine, and the outlet flow rate is going to be the same, 1 mole per second, right? Mass is conserved, or moles are conserved. But the pressure is going to decrease to 2 bar, and the temperature is also going to decrease to 400 Kelvin. Okay? As the methane passes through the turbine, we know that shaft work is going to be extracted from the system. And what we want to figure out is how much shaft work do we get out of the system if the methane goes from the stream 1 conditions to the stream 2 conditions. Okay? And so we could go through this problem using the same things that we've done before. And so if we go through the energy balance, we could show that the shaft work in the system divided by the molar flow rate is just going to be equal to the difference between the outlet molar enthalpy and the inlet molar enthalpy. Okay? All right, and by definition, this difference, we could describe this as, the integral of the total derivative of the enthalpy from its initial pressure and temperature to its outlet pressure and temperature. Okay? All right, so that's just, what the basic definition of the differences between two enthalpies are. Okay? Now, in order to, get a more precise understanding of what this means, we could apply, the tools of the calculus of thermodynamics to show that this integral, this dH from pressure 1, temperature 1 to pressure 2, temperature 2, we could show that this dH ends up being equal to this. Okay? So it's kind of a long equation. Should be a round parenthesis. Okay? Alright, and so using the calculus of thermodynamics, we could show that dH expands out to this. Alright? And so, we've seen this before in previous examples, where this dV dt, for this derivative, what one could do is just plug in an equation of state. And you could have an actual function in there. Right? But the other thing we need to remember with this function is that the Cp here, as we showed in the previous video, it's not just a function of temperature, but it's also a function of pressure or volume as well, right? And so, the fact that Cp is a function of many things complicates this integral, okay? All right, and so if we want to calculate the change in enthalpy of actual real fluids, we need to, account for that complexity in the heat capacity. And so there are a couple of different ways for approaching it and accounting for this complexity. One possible approach is based off of what I talked about in the last video, where we could just describe, molar heat capacity as the sum of our ideal heat capacity minus a term that accounts for non-idealities. Okay? So this ideal gas heat capacity is a function of only temperature, and it occurs when pressure goes to 0. And then the second term here, this accounts for the effect of pressure. Okay? Alright, and so what one can do is you could take this entire function, plug it in here, and then go out and do your integral. Okay? So that's a valid statement, and it can be done. But there is some risk in doing that. And the reason for that is because in the CP equation, we're dealing with a second derivative here. Okay? And in general, when dealing with second derivatives, you'll learn more about this in your computations course. But essentially, when you start putting in second derivatives into your equation, you'll find that they're going to be very sensitive to what I'll call errors in the model, or uncertainties. Okay? About the reason for that's a bit outside the scope of this course, but I'll just say that the second derivatives, if you plug in some sort of function in there and then take the second derivative of it, it's going to be very sensitive to errors, and as a result, that could create an inaccurate estimate. And so if you're trying to do this calculation to actually figure out how much work you could produce from your turbine, when you start dealing with these second derivatives, the estimate may become inaccurate. Okay? Alright, and so, I give that a little warning, but once again, I'll repeat that this approach could work, or can work, but if you try it this way, you have to be very careful. You got to be very careful with the second derivative. Because if you're taking the second derivatives of things, any errors in the model will get amplified. Okay? And this is especially true if you start using some of those more complicated equations of state, like the Penn-Robinson, or something that's a cubic equation of state. Okay? Alright? And so, dealing with second derivatives is kind of risky, and if we can, we would want to use a method that allows us to avoid taking second derivatives.